Hi, I'm Daniel.
I'm Kyle.
And we're going to talk about reversibility and magnetic reconnection.
Yeah, so magnetic reconnection basically involves a transfer of magnetic energy to kinetic energy in plasmas. And in this video here, you can kind of see what's happening. We've got opposing magnetic field lines. They come together, they reconnect, and then plasma is ejected out the sides here. And this is thought to be a driving mechanism behind solar flares, coronal mass ejections, and the northern lights. And in particular, we're interested in the reversibility of this process, both numerically
It's time
and...
to get out and go. But before you do, get into the highway.
So we're interested in numerical and thermodynamic reversibility.
Now, in order to study this, there are astrophysical plasmas that we can study with satellites, and there are lab plasmas, but both of those are pretty difficult to set the initial conditions you want and to arrange the magnetic fields as you need them. So what we do instead is we use simulations, and in particular we use a technique called particle and cell simulations, where we track individual particles in the plasma but only track aggregate electromagnetic fields. In all the simulations we're going to show you today, the initial condition will be, as you see above here, with a thin into-plane current sheet in the middle of the box. And after reconnection gets going, that current sheet develops into these two magnetic islands that you see in the lower panel.
Okay. So in studying the numerical reversibility, basically we do the following. We simulate a forward reconnection until some time t, at which point we instantaneously reverse all of the velocities and the directions of the magnetic fields, and then we let the system continue evolving. And if we had a perfect numerical simulator, what we'd expect is that the system would just go back to its initial conditions. But that's not what we end up seeing. So here we have the initial current sheet. And so we start to form this X line in the center here where the reconnection actually happens. And as plasma is ejected off to the sides, we start to see this formation of these magnetic islands over here. And then we reverse the simulation, and instead of going back to its initial current sheet, it just starts reconnecting in the forwards direction again. And so one way we can study how much reconnection has occurred is by looking at reconnected flux, which basically measures sort of how many magnetic field lines have been reconnected. And as we can see here, the flux is increasing, then we reverse it, and it goes back a little bit, but then just continues increasing again. And basically we think this happens because backwards reconnection is unstable. In forwards reconnection, the electric field and the out-of-plane current are parallel so that E drives J, whereas in backwards reconnection, E and J are opposite, so E opposes J. And we think that the instability is triggered just by numerical fluctuations. And we found that adding a guide field, which is a uniform magnetic field in the Z direction, helps with reconnection. As you can see this dashed line here. It reverses further and for longer. And we think this is either because it reduces the effect of the numerical fluctuations or reduces the growth rate of the instability.
Now, aside from our ability to run a simulation backwards, we could also talk about thermodynamic reversibility, which is usually what physicists mean when they say that a process is reversible. The thermodynamic reversibility refers to the probability of a process running in reverse over some large ensemble of systems, which for equilibrium systems, usually we choose the ensemble to be the ergodic measure of the system. Our system is highly non-equilibrium, and so the choice of ensemble is not obvious. The most common choice gives a form for the entropy that actually turns out to be conserved, so it can't tell us anything interesting about thermodynamic reversibility, at least in the collisionless case. So what we do is we use Zubarev's method as an algorithmic way of constructing an ensemble for which to study the probability of reversal. So we choose some observables to constrain the expectation values of, and then we construct the ensemble that maximizes entropy subject to those constraints. And we try to choose observables such that the entropy is doing something interesting and can tell us useful information about the dynamics of our system. For reconnection, we choose the magnetic field as our observable to constrain. And you can see what the entropy looks like with just the magnetic field constraint in these two panels here, with and without a guide field. We're still working on interpreting this quantity and studying the predictive use. And finally, we have some people we'd like to thank.
Okay, thank you.